Hi everyone, welcome you all to the Brilliant Group of Institution. Today we are here to discuss the most important MCQ, around 50 MCQ from the chapter Alcohols, Phenols and Ethers. As a part 1 video, here we are discussing 50 MCQ. In part 2 video, we will meet again with some more 50 MCQ. Okay, so here we can go to the first question for the chapter Alcohol, Phenols and Ether. Here we have the first question. Match the column 1 with column 2 and mark the appropriate choice. What is given in column number 1? Column number 1, they given so many, I think the common names are given, right? Catechol, resveratrol, paracresol and quinol. And there are corresponding structures also given here, right? So let us find out which is the matching one, right? You may study some common name. Let me tell you a small theory here. You know the benzene with OH is called what? Phenol. If one more OH group comes around the near position or the ortho position, we will call it as catechol, right? We will call it as what? Catechol. If the benzene ring with another OH group, again phenol, now you place one more OH group in the meta position, then we can call it as what? That is resveratrol, right? Resveratrol. Then, what about if it is on para position? If this OH group on phenol, if the OH group is on para position, then we can call it as what? Hydroquinone, or we can call it as quinol, right? Hydroquinone, or we can call it as quinol. All right. Now, so it's called what? Quinol. Now, what about the other one? Some other system you may study. The phenol again and CH3 group on the ortho position. That's a nearby. And another case, phenol in which CH3 on the meta position. Then another one, phenol and the CH3 on the para position. This is also a special name. If the compound contain phenol along with the CH3 group, if phenol with the CH3 group, we can call it as what? Cresol, right? So this is called orthocresol. Why it is called orthocresol? Because that CH3 are on the ortho position, right? Then this is in the meta position. Therefore, it is called metacresol. And what is this? Paracresol. So we can go to the answer. Catechol. Where is catechol? Where is catechol? OH are on adjacent position. Where is that? Here we have, this is compound A. Resveratrol. What is resveratrol? OH and OH are on meta position. This is resveratrol. Where is paracresol? Paracresol mean OH and CH3 are opposite. OH and CH3 are opposite. This is the paracresol. Where is quinol? Quinol mean OH and OH are opposite para. That is the first one, D. So which is the matching option? First one with the second. We have two options. Then the second one, B with the third one. A2, B3. Yes, let's go with option A, right? A2, B with the third one, right? B3. And what about C? C is with the fourth one, D is with the first one. Yes, option A is the correct one. Alright, so let's go to the question number 2. Here we have the carbon-oxygen-carbon angle in ether is about. Okay, simple question. Let me tell you a small theory here. You know a tetrahedral geometry. For example, you can consider, if you can consider methane, all right, methane. This is methane molecule. You know what is a geometry? Tetrahedral geometry. Then I'm taking a alcohol. Okay, this is a tetrahedral geometry. Now let me go to one water molecule. Let us consider one alcohol. All right, one alcohol. Okay, one alcohol, same like one water molecule. Here we have CH3OH. Let me take the compound example as methanol. All right, methanol. You know, oxygen containing 2 lone pairs. All right. Now we can discuss about the other one, ethers. What about ether? You know, ether, for example, CH3OCH3. What is the name? Methoxymethane. All right. Here, what are the bond angle in each system? Okay. In tetrahedral bond angle, what is a normal tetrahedral bond angle? you may study 109.5 degree, or you will study like 109 degree 28 minute, right? So here alcohol, what is the bond angle in alcohol, dear all? Alcohol, the bond angle is nearly 109 degree. Exactly, we can say 108.9 degree, but almost 109 degree. What is the bond angle? What is the bond angle in an ether? Ether, the bond angle is nearly 111.7 degree. 111.7 degree. Okay, now let's see what are the datas here. You know, normal tetrahedral bond angle 109.5 degree. In alcohol structure 109 degree. In ether it is little greater. Why? Why in ether the bond angle between carbon, oxygen, carbon is little greater? Little greater. There is a reason. Because you see, dear all, there is a methyl group. You know, methyl groups are bulky group. Bulky group should not come closer. They will repel. So CH3 repel each other. What will happen? The bond angle increases. So what is the answer here? This is a direct question. What is the carbon, oxygen, carbon bond angle in ether is about? It is nearly 111.7 degree. It is not exactly given, which is the almost correcting similar answer. We can go with option C, right? 110 degree. That is the bond angle in ether, right? Let's go to the third question. In third question, we have the carbon, oxygen, hydrogen bond angle in alcohol is slightly less than. Just in the previous question we discussed, what is the carbon, oxygen, hydrogen bond angle in alcohol? 109 degree, correct? So the COH bond angle in alcohol, you know, it is 109 degree. Now, it is slightly less than the tetrahedral angle. What is tetrahedral bond angle, dear all? We studied 109.5 degree. 109.5 degree. Whereas COC bond angle in ether, what is in ether bond angle? 111.7 degree. It is slightly greater. Because already we discussed why in ether the bond angle is slightly greater than the normal tetrahedral bond angle and like alcohol. So here what is the reason, dear student? Option A of the repulsion between the two alkyl R group. The alkyl groups are very bulky group. They will repel each other. So they will try to exist with a large distance and far apart. So there is a large difference in their bond angle, right? So option A is the correct one. Why ether shows greater bond angle? Due to the repulsion of alkyl group. Question number 4. Here we have an alkene. What is the alkene given here? CH3, CH, double bond CH2. What is this alkene? Propene. It is treated with B2H6. Dear all, in alcohol chapter, you may study the preparation of alcohol from alkene. First method you may study, that is called acid catalyzed hydration, right? We will add water. We will add water in presence of an acid. This is the second method of preparation of alcohol, same from alkene. How we can prepare? Hydroboration oxidation. What is the process called? Hydroboration, and then we have carried out oxidation. Yes or no? Yes. This is propene. This is the same example given in textbook. Propene, which is first treated, first process is hydroboration. What is mean by hydroboration? We are adding hydrogen and boron. Hydrogen and boron containing only one species we discussed in this chapter, that is diborane. What is diborane? B2H6. After that, we will add which one? Oxidation. We will add oxidation in presence of hydrogen peroxide, right? Hydrogen peroxide basic medium. So what will happen? Propene is the alkene. It is directly converted to propanol. This is the exact definition given in NCERT textbook. Alright. So let's go with option C. Propanol is the product. You will get it from the hydroboration oxidation of which compound? Propene. Alright. So next question, dear all. These are the question, most expecting type of that. Okay, when you're studying organic chemistry, very careful. We have to know what is the purpose of each and every reagents. Choose the correct X and Y in the given reaction. What is the product in first reaction and second reaction? That is the question. Let's see. You can see the first question. It is an NCERT in-text question. You can see there is a CO group, dear all. What is CO group? That is called ketone group. All right. Can you see here CO? But it is not ketone because COO is there. It is an ester. It is an ester. Very careful. It is an ester functional group. All right. This is a ketone. This is an ester. Now, what about the second compound you have? It's purely we have an aldehyde. All right. We have an aldehyde. Okay. What is the reagents we are using? NaBH4. What is NaBH4? Sodium borohydride. It is a reducing agent. It is a reducing agent. What is the purpose of NaBH4 in organic chemistry? For reduction, right? Is it using as a reducing agent, right? Yeah. It can reduce a aldehyde. It can reduce a aldehyde into primary alcohol, a ketone into secondary alcohol. That is the purpose of which one? NaBH4. Which one? NaBH4. All right. Is it having any action on ester? No. NaBH4 having no action on ester. Okay, keep in mind all of you. So we no need to disturb ester. We no need to disturb ester. Please don't touch ester part because NaBH4 having no function on ester. Alright, so ester, let me keep it like this. Ketone converted to alcohol, right? Ketone. So let me write your product here. This will be like this. Ketone converted to alcohol. This part, no changes. We will get as it is. Okay, fine. What about the second one? Aldehyde converted to primary alcohol. We will get CH3CH2, CH3. We have CHO converted to what? CH2OH. It converted to primary alcohol. That's it. This is what happening. Can you find out this X and Y in this option? Where is X and Y located? I think option C, right? Option C. In option A, they didn't make any changes in ketone. Option B, they reduce ester also. Should not do that. But here, yeah, they reduce the ketone. Ester, they didn't do anything. And alcohol, yes. Option C is the correct answer. Let's go to the next question, dear all. Here we have. Which reducing agent is used for the following conversion? What all reducing agents you studied? I hope you studied hydrogen in presence of a catalyst like nickel, platinum, palladium catalyst, correct? Some other things are like, NaBH4, sodium borohydride. And the strongest reducing agents, you know that, which one? LiAlH4, lithium aluminium hydride. It is the strongest reducing agent, correct or not? Yeah. So which reducing agent is used for the following conversion? If we have a general data, hope you studied already. Generally, primary alcohol on oxidation, we will get aldehyde, correct or not? Primary alcohol on oxidation, aldehyde. So aldehyde on reduction, primary alcohol. And aldehyde further oxidation, what you will get, dear all? Carboxylic acid, you will get it. Correct. Similarly, what about secondary alcohol? Secondary alcohol on oxidation, we will get ketone. Right? Ketone on further oxidation, again carboxylic acid. What about tertiary alcohol? Tertiary alcohol will not undergo oxidation. You know that, right? Okay. So which reducing agent? This is oxidation. So what is reduction? Carboxylic acid, if you want to convert into aldehyde, that is reduction. Aldehyde, if you want to convert into primary alcohol, that is reduction, right? Forward reaction is oxidation. So of course, backward reaction, reduction. Which reducing agent is used for the following conversion? What you have to convert here? One acid you have to convert into primary alcohol. One carboxylic acid, if you want to convert into primary alcohol, we have to carry two steps, right? Two reduction need to happen. So we have to use a strongest reducing agent. Which is the strongest reducing agent here? Lithium aluminium hydride is the strongest reducing agent. So let's go with option A. A is the best reagent. NaBH4 cannot reduce carboxylic acid directly into alcohol. Okay, K2Cr2O7 and potassium dichromate and potassium permanganate, you know, they are strong oxidizing agent, not a reducing agent. Okay, careful. Next one. 1 mole of ethyl acetate. You know, ethyl acetate is an ester. What is ethyl acetate formula? Ethyl. Okay, ethyl acetate. All right, ethyl acetate. Oxygen is there. Ethyl acetate. It's an ester. So ethyl acetate. This is the compound ethyl acetate. Ethyl group is there. Acetate group is there. Right. It is formed by the, you know, ester is formed by the combination of a carboxylic acid and alcohol, right? Yeah. This is the alcohol part. This is the acid part. All right. Now, which is on treating with excess amount of lithium aluminum hydride. All right, it is happened lithium aluminum hydride. It is a reduction. Ester you can reduce through lithium aluminum hydride. It is very easy to write the product. Ester on reduction, you will get alcohol. How many alcohol? 2 alcohol. Keep in mind, all of you, dear all. A ester on reduction, you will get 2 alcohols. It is very easy to write the product. Let me show you. How many carbon are present left side of this oxygen? A short trick, okay? A short trick. On this oxygen, how many carbons are there? 2 carbon. Okay, 2 carbon. Which is the 2 carbon containing alcohol? That is nothing but ethanol. So one of the product is what? Ethanol plus. How many carbon right side of this oxygen? Again 2 carbon. So 2 carbon containing alcohol. Again ethanol is the product. So how many alcohols are producing? 2 alcohols are producing. Both alcohols are which one? Ethyl alcohol or ethanol. So what is your answer? Ethyl acetate on reduction, you will get 2 moles of ethyl alcohol. Option C is the correct answer. Alright, next question, dear all. It's for you. Tertiary butyl alcohol can be prepared by the reaction of, very important, you may study the preparation of alcohol from Grignard reagent, right? You know, a Grignard reagent, this is the general thing. Any Grignard reagent, when you treat it with methanol, what is methanol is also called formaldehyde. Formula, you know, HCHO, followed by hydrolysis. Grignard reagent, when you treated, any Grignard reagent, when you treated with the methanol as a compound, you always will get a primary, that's a primary alcohol. You can fix the product, okay? Any Grignard reagent, when you treated with methanol or formaldehyde, always you will get primary alcohol. Then, any Grignard reagent, when you treated with other aldehyde except methanol, any other aldehydes, if you are choosing, you can prepare a secondary alcohol. Then how you can prepare tertiary alcohol? It's so easy. Grignard reagent, you can treat it with any ketone. You will get always tertiary alcohol, generally. Okay, this is the general method. Now, tertiary butyl alcohol. What is tertiary butyl alcohol? You know, this is tert-butyl group, right? With an alcohol is called tertiary. It is a tertiary alcohol, right? Because OH connected carbon directly connected to 3 carbon. It is a tertiary alcohol. Alright. So, if you want to get a tertiary alcohol, what all things should be react, dear all? Grignard reagent should react with a ketone. Okay. Option A is possible? No. Because it is acetaldehyde. What is acetaldehyde? Ethanol. Acetaldehyde with a ethyl magnesium iodide Grignard reagent, you won't get it. You will get secondary alcohol. Correct. Acetone. What is acetone? Propanone. What is acetone, dear all? Propanone. CH3CO, CH3. Propanone, when react with the methyl magnesium iodide. This is the Grignard reagent. Yes, here you can get it a tertiary alcohol. A ketone reacting with the Grignard reagent, you will get a tertiary alcohol. Option C possible? No. Formaldehyde. If you are treating formaldehyde, what you will get? Methanol, primary alcohol. Butanol, that's also possible, right? butanone and methyl magnesium iodide, because butanone also one of the ketone. What is butanone? What is butanone? CH3CO, CH2, CH3. Correct. Plus, it is reacting with what? Methyl magnesium iodide, CH3MgI. We can avoid this one. Why? Because how many carbons are in your ketone? 1, 2, 3, 4. How many carbon in your Grignard reagent? 1. Total 5 carbons are there. You will get it in your product. But do you need 5 carbon in your product? No. 1, 2, 3, 4. Only 4 carbon is enough. This is getting from only acetone, because acetone contain 1, 2, 3 carbon and the Grignard reagent contain 1 carbon. Total 4. So option B only the matching one. Here we have the next question. The same question but another way. Propanone on reaction with alkyl magnesium bromide followed by hydrolysis will produce what we said now. Dear student, propanone. Propanone is also known as what? Acetone. Propanone, when it is reacting with a Grignard reagent. Generally, when a ketone reacting with a Grignard reagent, your product will be tertiary alcohol, right? Tertiary alcohol. So propanone is a ketone. When it is reacting with the alkyl magnesium bromide, that is your Grignard reagent, you will get always tertiary alcohol. Understood or not? Alright. Next one, let's go. In the following sequence of reaction, identify what is the compound Q. Final product we have to find out. So easy method. You know the beginning, starting material they given as benzene. Alright. Benzene treating with the what? Oleum. You know what is oleum, right? H2S2O7. What is mean by oleum? Fuming sulfuric acid. You may study the structure everything in the chapter P block. Correct. Benzene on oleum. You will get what? Benzene with SO3H. Benzene sulfonic acid. Benzene sulfonic acid. Alright. Now, second method, what they are using? First, they are treated with the sodium hydroxide. Second, they are treated with the acid. Dear student, what is your product? That is nothing but phenol. This thing you have studied in the preparation part of phenol. Let me remind you, you have studied total 4 methods of preparation of phenol in NCERT textbook. What is the first method? Can you remind? First method is Dawes process. Chlorobenzene you can convert it into phenol. That is called Dawes process. Second method, this one. Benzene converted to phenol. First one oleum, then NaOH and acid. Third method is from aniline. First diazotization, then treating with the warm water. The fourth method from cumene, right? Cumene. These are the total method. So this is nothing but it's a preparation of which one? Phenol. Answer is which one? Option B. Your final product is what? Phenol. Right. Next one. Let's go to the next one. Cumene on reaction with the oxygen followed by hydrolysis gives again phenol. Right? Because cumene reacting, you know, from cumene we studied only one reaction to prepare what? Phenol. Let me write the reaction. What is mean by cumene, dear all? A benzene with a isopropyl group. This is called cumene. Benzene with a isopropyl group is what called cumene. First of all, oxidation, we will add oxygen. Very simple way you can able to understand this process. Can you see this one? There is a carbon and there is a hydrogen. Correct or not? Okay. Can you see oxygen atom? Oxygen molecule is there. There are 2 oxygen atom. You please place these 2 oxygen atom in between this carbon and hydrogen. So let me write like this. Benzene, C, CH3, CH3. What we can write? OOH. Just add the oxygen atom in between this carbon and hydrogen. Alright. Now, so what is the name of everything you may study? Cumene hydroperoxide, because peroxide linkage is there. What is the last step? Acid hydrolysis, treating with H3O+. Very simple way you can able to remember the product. You please take this OH group directly add to the benzene ring. What you will get? You will get phenol, OH. Okay. This OH group, you please, it's only to remember, okay? Just a short trick. Take this OH group and just add into this benzene. What is left in the system? CH3, C, CH3O. So product is CH3CO CH3. What is the byproduct? This is an expecting question for exam. What is the byproduct formed in the preparation of phenol from cumene? What is the byproduct? That is acetone or propanol. So during this reaction, what all compounds are forming? Phenol and acetone. Phenol and acetone. Option D is the correct answer. Alright. Next one, dear all. Which of the following reaction will not yield phenol? Through which reaction you cannot prepare a phenol? That is the question. Okay. Option A, chlorobenzene. You studied now dose process, right? Dose process. What is dose process? Chlorobenzene first treated with the NaOH, aqueous NaOH. You will get sodium phenoxide at a 623 Kelvin and 300 atm pressure. Yeah, 300 is specified. And second reaction, you know, acid hydrolysis. Yeah, we were adding HCl. So you will get phenol. It's a method. Question which is not a method. Okay. Aniline, yeah, aniline first of all diazotization, we will get benzene diazonium chloride. Then we are treating with the warm water, we will get phenol. Yes. Benzene, just to be discussed now, treating with the oleum, then NaOH and H+, we will get phenol. So the expecting answer is option D. Why? Chlorobenzene, okay, aqueous NaOH, fine. But is it carried out at 298 Kelvin and 1 atm pressure? No, 623 Kelvin and 300 atm pressure. That is a condition in dose process, right? So this is not a method. This is the answer through which one you cannot prepare phenol. Next one. Which of the following statement is not correctly, okay, very careful, not correctly showing the trend of the properties? Option A. What is this? Ethanol, propanol, butanol. Solubility order is given. They are saying that ethanol having very high solubility than butanol. Is it correct? Yes. Because we studied as the carbon number increases, solubility decreases, because carbon compounds hydrocarbons are non-polar. Water is polar. Correct. So as the number of carbon increases, solubility decreases. Correct statement. But question is, which is not correct? Option B, ethanol, propanol, butanol, boiling point. They are saying ethanol having very less boiling point than butanol. Of course, right? Butanol surface area greater, more carbon atom, more mass, more boiling point. Correct order. Option C, propanol, 2-methyl propanol, and here 2-methyl propan 2-ol. What the option given? Boiling point. The property is boiling point. Is it correct? We know they are actually isomers. Not isomers one, we can say that. Actually, they should be given here butanol here, right? Then only they will all of them converted into the what we can call the isomers. Okay. Anyway, this is a linear one. There is a branch. There are two branches. Correct? There are two branches. You know, as the number of branches increases in the system, what happens to boiling point? What happens to boiling point? As the number of branching increases, the boiling point decreases. Yes, it having two branches, so boiling point decreases. Correct one. What about option D? The same compound they given in just opposite order, boiling point. This is wrong, dear all. This is your correct answer. Because here you can see more branches are there, and they having greater boiling point. No. We studied more the number of branches, less surface area, less boiling point, right? So this is the wrong statement given here. Okay, shall we go to the next one? Yeah. Arrange the following compound in the increasing order of their boiling point. What is the first compound? Propan 1-ol. I'm not writing completely. Okay, propan 1-ol means 3 carbon with an alcohol. What is the next compound? Butan 1-ol. 1, 2, 3, 4 and 1 alcohol. Butan 2-ol. 1, 2, 3. Okay, second carbon if you consider 1, 2. Butan 2-ol. And pentan 1-ol. 1, 2, 3, 4, 5. 1-ol. Question, boiling point. Same reason. You know, alcohols having generally greater boiling point. What is the reason? They can make very strong intermolecular hydrogen bonding. Therefore, If you consider this compound, let me take this is number 1, number 2, number 3, number 4 compounds. Which one you expect having greatest boiling point? Of course, I hope your answer will be the fourth one, pentan 1-ol. Why? Because they contain 5 carbon atom, greater mass, as well as all carbons are located in the straight chain, greater surface area. So fourth one having greater, which means pentan 1-ol having greater boiling point. Question is increasing order. So where you can see pentan 1-ol, definitely we can cancel option C and D because they given greatest boiling point is propan. No, either pentan 1-ol. Yeah, option A or B. Okay, so pentan 1-ol over. Now next one, dear all. Compound number 1 contain only 3 carbon and alcohol. Hydrogen is also there. And second one contain 4. So greater boiling point is for which one? You know, second one and third one are isomer. Among second one and third one having greater boiling point because they having more straight chain, no branching. No branching mean more greater, which one? Boiling point. So after fourth one, we are expecting butan 1-ol first one. Where is butan 1-ol? Yeah, after pentan 1-ol, butan 1-ol greater, option A. But here given pentan 1-ol, then butan 2-ol. No. So after pentan 1-ol, we can go with which one? Pentan 2-ol, then propanol. Yeah, the correct answer is given in option A. So this is the point. Generally, alcohols having greater boiling point because of intermolecular hydrogen bonding. The main thing or the main reason why branching, branching increases. If number of branching increases in the system, definitely their boiling point decreases. What is the reason? Surface area decreasing if the branches increases. Okay, so let's go to the next question here all. Orthonitrophenol is less soluble in water than para and metanitrophenol because what is orthonitrophenol? This is called phenol and ortho position there is a nitro group, NO2 group. You have studied that in orthonitrophenol there is a intramolecular hydrogen bonding, right? Intramolecular hydrogen bonding. What is mean by intra? Within the molecule there is a hydrogen bonding, right? What about para and meta, dear all? You consider para, right? This is called para nitrophenol, right? This is para nitrophenol. Is it possible to make a hydrogen bonding here? This hydrogen and this oxygen, is it possible to make a bond? No. So let me take one more para nitrophenol. One more para nitrophenol. Okay. Now any chance to make a hydrogen bonding? Yes, there is a chance. Where is that? Here, this hydrogen and the single bonded oxygen can make a bond. Here the hydrogen bonding is between 2 molecules. Here the hydrogen bonding is happen within the molecule. Here the hydrogen bondings are between 2 molecules. Therefore, they are called what? Intermolecular hydrogen bonding. Which is the strongest bond? Which is the strongest bond? Inter. This is the stronger one, dear all. This is the stronger hydrogen bonding. Intra is the weaker hydrogen bonding. Okay, keep in mind. Now come to the question. Why in orthonitrophenol they are less soluble in water? If you want a compound to soluble in water, they should have an ability to make very strong hydrogen bonding with the water. But intramolecular hydrogen bonding is a weakest bond in orthonitrophenol, so they can less soluble in water. Correct. So what is the answer, dear all? Option A, orthonitrophenol shows intramolecular hydrogen bonding. Yes, intramolecular. Because of that, it is less soluble in water. Option B, orthonitrophenol show inter. No. Melting point of orthonitrophenol is lower. Melting point is not a factor here. Orthonitrophenol is more volatile in steam than those of meta and para isomer. That's also one of the correct definition. But the correct answer why orthonitrophenol is less soluble in water mean they cannot make a strong hydrogen bonding with the water because they're having a very weak intramolecular hydrogen bonding. Alright, next one. For the reaction, what's the reaction given? Ethanol. They given C2H5OH, ethanol, reacting with a hydrogen halide and it's giving what? C2H5X, ethyl halide along with the water. Alright, simple reaction. You know, C2H5 here, positive part, OH is the negative part. Here H plus and X minus is there, a double displacement, you know, like a nucleophilic substitution. Here OH minus and X will interchange. You will get, you know, how to convert a alcohol into haloalkane. Correct. If you add HCl in presence of anhydrous zinc chloride, that is called Lucas reagent, right? Yeah, a alcohol can react with the hydrogen halide. It can give you haloalkane. Question is, which hydrogen halide can undergo the reaction here faster? You know that they given HCl, HBr, HI. You know, HCl, HBr and HI. Which bond is, or which species is more reactive in almost all reaction? HI. Why HI is more reactive? You know that. You know, HCl bond is little stronger bond. HBr, you know, while coming down the group, size of the atom increases. Size of the atom increases mean the strength of the bond weaker. The strength of the bond what? It's a weakest bond. If it is a weakest bond, you can break it so easily. You can convert it into the product. It can undergo reaction easily. So, which is the most reactive one, dear all? HI is most reactive. Then HBr. Then we can go with HCl. What is your answer? HI, HBr, HCl. Option B is the correct one. So, right. So, down the group in hydrogen halides, reactivity increases. Now, next question we can have. Arrange the following alcohol in the order of increasing reactivity towards sodium metal. It's an indirect question, okay? Compound number 1, let me take CH3 thrice COH. And compound number 2, that is CH3. Okay, let me just expand the structure. Okay, let me just expand the structure. Tertiary group, let me write like this. Okay, first compound CH3 thrice C with the OH group. Okay. Second one is CH3 CH, CH3 OH. Alright. And compound number 3 is what? CH3 CH2 OH. Okay, fine. What is the first one? Question, which will react with the sodium metal fast? What will happen when it is treated with a sodium, dear all? What will happen if you treat it with a sodium? You know, alcohols are acidic in nature. So this hydrogen, it can leave it as what? H plus ion, right? H plus ion. You know, sodium is a highly reactive metal, so it can displace this hydrogen. So, which is more acidic in nature, it can react with the sodium very fast. So, we are indirectly asking you in this question, which is most acidic in nature. Which is most reacting with the sodium mean they are indirectly asking you, which is more acidic in nature. Which is more acidic in nature? If you consider tertiary, secondary, primary alcohol, what group is present here, dear all? You know, alkyl groups. Alkyl groups are which type of group? Electron donating group. Here there are 3 electron donating group nearby OH. There are 2 electron donating group nearby OH. There is a 1 electron donating group here almost. You know, what is the factor affecting acidity? Electron withdrawing group, if it is there, it will increase the acidity. Electron donating group, if it is there, they will decrease the acidity. Electron donating group will decrease the acidity, dear all. So, here there are so many electron donating group, so the acidity is very less acidity. So, which one having more acidity? They contain less number of electron donating group. This is more acidic one. Okay, this is more acidic one. Finish. So, what is your answer, dear all? You know, among primary, secondary, tertiary alcohol, which is the most acidic one? Primary is the most acidic one. Okay. So, primary greater than, secondary greater than, tertiary. That is the order of acidity in primary, secondary, tertiary alcohol. So, what is your answer? Which will undergo acidity more? Third one, then second, then first one. So 3, 2, 1, 3, 2, 1. Option C is the correct answer. So careful when they are asking you whether which compound is more reactive towards sodium or something. They are indirectly asking you which is more acidic in nature. Okay. Next question. We have Out of 2-chloroethanol. What is 2-chloroethanol, dear all? Ethanol means 2 carbon with an alcohol. Second position, there is a chlorine. This is called 2-chloroethanol, right? CH2, CH2. Okay, this is 2-chloroethanol. And ethanol. What is ethanol? CH3, CH2, OH. Which is more acidic and why? Which is more acidic and why? Let's see. Very simple question. What is the major difference between these two compounds? There is a extra chlorine. Chlorine halogens are which type of group, dear all? They are electron withdrawing group, right? They are more electron negative element. They are electron withdrawing group. Okay. Which is more acidic. Alcohols, more acidic in nature generally. So, which means it can lose this H plus ion. So, here there is an electron withdrawing group, correct? Electron withdrawing group. What is the major factor affecting acidity? Electron withdrawing group, if it is there, they will increase the acidity. Electron donating group, if it is there, they will decrease the acidity. Alright? They will decrease the acidity. Okay, dear all of you. So, electron withdrawing group, if it is there, this is more acidic. So, we can say this is more acidic in nature. What is the reason? There is an electron withdrawing group. Electron withdrawing groups belongs to which category? Minus I effect. Which category? Minus inductive effect group. Electron donating groups are plus I effect group. Electron withdrawing groups are minus I effect group. Minus I effect. Okay. So, what is your answer? Question 2 are there. Which is more acidic? What is your answer? 2-chloroethanol. What is the reason? Minus I effect of chlorine. Your answer is what? Option C is the correct answer. Clear all? Shall we go to the next one? Okay, next question. What is the correct order of strength of acidity of the following compound? Most expecting type of question, dear all. Phenol. All of the compound contain phenol. Phenol is more acidic in nature. Why phenol is more acidic in nature? You may study the reason. This is called phenol. When phenol lose this hydrogen as H plus ion, the remaining compound is called what? Phenoxide ion. Phenoxide ion. It is highly stable due to resonance. So, phenol is ready to lose hydrogen fast. So, all of them contain phenol. So, all are best acidic one. But the factor affecting acidity we already discussed. Once again I am repeating. Electron withdrawing group, if it is there, it will increase the acidity. Electron donating group, if it is there, they will decrease the acidity. You know what are electron withdrawing group and donating group, right? For your reference I am just giving. Electron withdrawing groups are generally nitro group, cyanide group, acid group, keto group, aldehyde group, etc. Electron donating groups are generally alcohol, amines, all alkyl groups, methyl, ethyl, etc. Okay, and another one, alkoxy group. Alkoxy, for example, methoxy, ethoxy. All kind of groups are which one? Electron donating groups. Okay, you see all of you here. In the first compound, just pure phenol. Okay, nothing to disturb or to increase the acidity or decrease the acidity, no factor. But here you can see there is a methyl group in the para position. Methyl groups, alkyl groups are which group, dear all? Electron donating group. So, acidity will decrease than phenol. What do you have here? Nitro group. Nitro group is a strong electron withdrawing group. What about here? There are 2 electron withdrawing group. So, as the number of electron withdrawing group increases, acidity automatically increase, right? So, which one having greater acidity? Fourth one. After that, third one. 4, 3. Then, in the first and second compound, when you consider which one having greater acidity? First one. Because second one contain a electron donating group, it will decrease the acidity of phenol. Okay. So, 4, 3, 1, 2. 4, 3, 1, 2. Where is answer? 4, 3, 1, 2. 4, 3, 1, 2. That is option D. Alright. 4, 3, 1, 2. Clear all of you? Right. Next one. Next question. Para-nitrophenol is a stronger acid than phenol. Okay, what is para-nitrophenol? We have, this is called phenol para position nitro group. This is called para-nitrophenol. It is a stronger acid than phenol. It is a stronger acid than phenol. They already said it is a best stronger acid. Okay. While para-cresol, what we studied, para-cresol, cresol mean phenol with a CH3 group. Para means para position. Okay, this is called para-cresol. So let me conclude. Para-nitrophenol, it is more acidic than phenol. What is the reason, dear all? Because it contains a electron withdrawing group. And than phenol, while para-cresol is a weaker acid than phenol. Yes, because it contains an electron donating group. Correct. What is the reason we can assign? Okay, let me discuss here. This is an electron withdrawing group. This is an electron donating group. What is the principle? Electron withdrawing group will decrease or increase? It will increase the acidity. Electron donating group will decrease the acidity. What is your answer? Option A. CH3 group decreases the electron density. Okay, let me just discuss. Actually, why? If there is an electron withdrawing group, why they increase the acidity or how they can increase the acidity? Let's discuss. If there is an electron withdrawing group, what is an electron withdrawing group? They will try to take all the electron from the whole ring towards that. They are trying to pull electron all towards that group. So you can see there is a bond between OH, right? These electrons also try to come closer to nitro group. So if there is an electron withdrawing group in the system, they will try to pull all the electron from the ring towards nitro group. So OH bond strength decreases, because those electrons also have a tendency to come towards nitro group. So this bond becomes weaker, dear student. If it is weaker, you can donate this hydrogen ion so easily. So it is more acidic, therefore. What about CH3 if it comes? If there is an electron donating group, they are donating electron towards the benzene ring. So OH bond become very stronger. More electron richness in OH bond, so it is very difficult to remove hydrogen. So it is less acidic. Come to the point. Option A, CH3 group decreases the electron density on oxygen hydrogen group. Is it? No. CH3 group will increase because they are giving electron towards OH group. It will increase the strength. No. Option B, nitro group decreases the electron density on oxygen hydrogen bond, making para-nitrophenol stronger. Yes, that is the correct answer. Option C, CH3 group increases the electron density on OH group, making release of H plus easier. No, CH3 giving electron, okay fine. By the way, OH bond becomes stronger, you cannot donate H plus ion. Okay, so I think best answer is which one? Option B itself. Next one. An unknown alcohol is treated with Lucas reagent. You know what is Lucas reagent, right? Concentrated HCl with anhydrous zinc chloride is called Lucas reagent. You know, Lucas reagent we are mainly using to distinguish between primary, secondary, tertiary alcohol. Correct or not? Yeah. To determine whether alcohol is primary, okay. Which alcohol react fastest and by what mechanism? So let me discuss a small theory here. You know what is Lucas reagent? It is a mixture of concentrated HCl with anhydrous zinc chloride. This is called Lucas reagent. You may study when a primary alcohol react with the Lucas reagent and secondary alcohol and tertiary alcohol, what are the reaction? Which will react faster with the Lucas reagent? Tertiary. Tertiary alcohol will give you a immediate turbidity, right? It will give you turbidity or the reaction faster, immediately. And what about secondary? Secondary will give you reaction after 5 minutes. After 5 minutes means its reactivity little lesser. Okay. What about primary alcohol? What about primary alcohol? It won't react under normal condition. It can give turbidity only by heating. only by heating, which means it is very less reactive. Okay, the question, which alcohol react fastest? Which alcohol reacting faster? Tertiary alcohol. Tertiary. So your answer either option A or option C. Next confusion, whether it is following SN2 or SN1 mechanism. Simple. You know tertiary alcohol. What is a tertiary alcohol example? Right, this is tertiary alcohol. Correct. It is treating with what? Lucas reagent. What is Lucas reagent? HCl with a zinc chloride. Right. What is actually happening here? This OH is eliminated as water. Chlorine will substitute. You will get tert-butyl chloride. Okay. First step is what? OH removing. If this OH leaving from the system, what is the charge getting by this carbon? Positive. It is a carbocation, right? What is carbocation stability order, dear all? Tertiary greater than, secondary greater than, primary. So, carbocation stability depends on SN1 or SN2 mechanism. SN1 mechanism. SN2 mechanism only follows which one? The steric rowdiness, right? More the steric rowdiness, less SN2 mechanism. Here the stability of carbocation we are checking because in this reaction, first OH group is leaving and by the way forming a carbocation. So what is happening? What is happening? It forming a tertiary carbocation. Tertiary carbocation. You know what is the order of SN1 mechanism? Tertiary greater than, secondary greater than, primary. Clear all of you? So what is the answer? Tertiary alcohol through SN1 mechanism. Option C is the correct answer. Next one. Which of the following alcohol react most readily with the Lucas reagent? Same question another way. You know Lucas reagent test is most given by tertiary alcohol. Which is a tertiary alcohol? That's a question. See how to identify alcohol, whether it is primary, secondary, tertiary, you know very well. If the alcohol connected carbon, if it directly connected to only one carbon, you can call it as primary. If the alcohol connected carbon directly connected to two carbon, it is called secondary. If the alcohol connected carbon directly connected to three carbon, it is called tertiary. If the alcohol connected carbon directly connected to one carbon, again primary. So which is a tertiary alcohol? Option C, it will give you reaction with the Lucas reagent faster. Next question, dear all. Dehydration. You know, alcohols can undergo dehydration in presence of strong acid, concentrated hydrochloric acid, like that, right? Dehydration of the following increases in the order is. First compound, let me take it, dear all. That's nothing but phenol. Alright, phenol. Okay. Second question, second compound they given, it's a normal cyclohexanol, alright. Third compound they given a cyclohexenol, right, a alkene is there with an alcohol, okay. Fourth compound, diene, okay, two alkenes are there. What is the alkene? Okay, here, this is the compound, okay, fine. Which compound will undergo dehydration faster? Let me see, give you a simple idea about dehydration. If you consider ethanol, what is ethanol? CH3CH2OH. What is dehydration? You are treating with the strongest acid, like a concentrated hydrochloric acid, sulfuric acid. Okay. What is mean by dehydration? You know, alcohol you have to take from alpha carbon. One of the hydrogen you have to take from beta carbon. Make a double bond between alpha beta. That's it. Once again. Alcohol you have to take from, you know, the main functional group is OH. OH directly connected carbon is called alpha carbon. Alpha carbon nearby carbon is called beta carbon, right? So OH group you take from alpha carbon. One of the hydrogen you take from beta carbon. Make a double bond between alpha beta. Your product is what? Ethene plus water. Dehydration. So generally, when a alcohol undergo dehydration, always you will get the compound alkene. What? Alkene. Okay. Actually, why they are undergoing this reaction, dear all? To attain stability, correct? So after alcohol converted into alkene, if the alkene is more stable, then only the alcohol is ready to undergo the reaction. Correct? Yeah. So let's see which will undergo reaction faster. Let me do dehydration in phenol, okay? OH group I am taking from alpha carbon. one of the hydrogen I am taking from beta carbon, put a double bond between alpha beta. Will they be stable? No, right? Phenol is already stable due to resonance. If you make one more double bond here, what happened? The conjugation, the resonance, everything will be disturbed. So phenol is not ready to undergo dehydration. What about this compound? Let me take OH group from alpha carbon, one of the hydrogen from beta carbon. So let me place a double bond between alpha beta. This is the product, cyclohexene. Let me write a OH group from this alpha carbon, one hydrogen from the beta carbon, put a double bond between alpha beta, your product will be this one, a diene. Again, OH you have to take from alpha carbon, one of the hydrogen you take from beta carbon, put a double bond between alpha beta, your product will be this one. Now you can able to understand which compound is more reactive towards dehydration. Which one, dear all? I think your answer is fourth one. Because fourth compound when undergo a reaction, thus dehydration, what is the product you are getting? Benzene. You know benzene is stable, right? Due to resonance. So fourth one will undergo reaction faster. What about second one and first one? Second one, at least a resonance is possible, right? If this double bond comes here, this double bond can be shifted. At least a resonance is possible. A small conjugation is possible. So it can be little stable. So third one. Is it possible in second one? No resonance possible. But least one, definitely the first one. Because phenol will not undergo dehydration. Because phenol already stable compound. It's not ready to make it to a unstable state. So what is the answer, dear all? 4, 3, 2, 1. Option A is the correct answer. Okay, next question. An alcohol X on reheating with concentrated sulfuric acid gives an alkene Y. Of course, when an alcohol on dehydration, you will get an alkene, which can show geometrical isomerism. What is geometrical isomerism? Cis-trans isomerism, correct? Cis-trans isomerism. Let me try with the compound number A. What is compound number A? CH3, CH2, CH, OH, CH3, correct? Butan 2-ol is the compound. First of all, it's reacting with a concentrated sulfuric acid. Dehydration will happen. What is dehydration, dear all? Take your alcohol from alpha carbon. Unfortunately, there are two beta carbon, right? This is one beta carbon. This is one beta carbon. Which beta carbon from which you are ready to take a beta hydrogen? I hope you will take from left beta. You have to make a double bond in the more crowded area according to Zaitsev rule. Right? According to Zaitsev rule, you can take hydrogen from here. You can make a double bond. Then it is but1-ene. Or you can take one hydrogen from this beta, you can make a double bond here, that is but2-ene. Which is the major product, but1-ene or but2-ene? But2-ene is the major. Why? Why? According to Zaitsev rule, double bond try to make always in a more crowded area. Or more substituted alkenes are more stable. That's what we studied. Correct? Yes. So please prefer this beta hydrogen. So let me take this hydrogen and I'm going to make a double bond here. I will get the compound CH3, CH double bond, CH single bond, CH3. What is the compound? But2-ene. Alright. Question. Is it this compound can show geometrical isomerism? Yes, it is possible. You know, this is C double bond C carbon. C double bond C. On the left carbon, there is one hydrogen, one methyl group. Okay, one hydrogen and methyl group. On this carbon also one hydrogen and methyl group. Yes or no? Yes or no? Can it show geometrical isomerism? Is it cis or trans? Yes. You can see CH3 are on same side. Hydrogen are on same side. Which form is this? This is cis form. If there is a cis, there will be a trans. Correct or not? How to draw the trans isomerism? Hydrogen opposite, methyl opposite, that is called trans. Cis-trans isomerism is also known as geometrical isomerism. So the first alcohol itself can give geometrical isomerism. Option A. Next one. The most suitable reagent for the conversion of RCH2OH. What is this compound actually? A primary alcohol to what? RCHO, aldehyde. Which is the best reagent to convert primary alcohol into aldehyde? Dear all, you know, primary alcohol converting into aldehyde is known as oxidation process, right? Oxidation. Which is the normal oxidizing agents we are studying? We are using PCC. What is PCC? Pyridinium chlorochromate. Or we are using anhydrous CrO3, chromium trioxide. Or we are using copper at 573 Kelvin. These are the best oxidizing agents. Any one of them you can choose it to convert primary alcohol to aldehyde. But the question, which is the most suitable? Which is the most suitable method you studied? PCC. PCC is the best reagent to convert a primary alcohol into aldehyde. Keep in mind all of you, all of them can be used. Okay. I'm not saying anhydrous CrO3, copper 573 can't use. All of them can be used to convert primary alcohol to aldehyde, but the best reagent is PCC. Alright, so your answer is which one? Option D is the correct answer. Next one. In the following reaction sequence, what is final compound Z? Let's carry out. What is the starting material? CH3CHOH, CH3. Propan 2-ol, which is on oxidation. Yes, student, propan 2-ol is a secondary alcohol. Secondary alcohol on oxidation, we will get ketone. So, what is a ketone? This is the ketone forming. What is a ketone, dear all? Name what is that? Propanone, right? Propanone. Next one. This is the compound Y. Alright, this is the compound Y. It's reacting with CH3MgBr, methyl magnesium bromide. That is the Grignard reagent. Second, they are treating with the acid hydrolysis. Okay, let me carry out this reaction first. You know, we already studied that a ketone, when react with a Grignard reagent, always you will get tertiary alcohol. So you can fix it your product always. It's a tertiary alcohol here, right? Let me write the mechanism. You know, Mg is the metal atom here. So this is the positive part, cation. This is the anionic part. So MgBr is the cationic part. CH3 minus is the nucleophile. This nucleophile will come and attack to this carbon. This O becomes O minus. What is the answer we can write here? CH3, CCH3. Okay. CH3, CCH3, double bond O becomes O minus. To this carbon atom, what attacked? CH3, okay. To this O minus, what will comes? MgBr will attack. Mg plus Br will attack. What is the last step? Acid hydrolysis. We are adding water, dear student. Water containing two species, right? Water containing two ion. What are they? H plus and I minus ion, or the OH minus ion. In H plus, so when you are adding to this cation and anionic region, when you are adding acid hydrolysis, very simple. H2O containing two ion, H plus and OH minus. You please add H plus into the negative part, OH minus into the positive part. Product is ready. This is actually byproduct, no need to bother. What is the major product? CH3, CCH3, CH3, OH. You see, we are getting a tertiary alcohol. We know already it is a tertiary alcohol, right? Yeah. What is the name of this product, dear all? We can suggest here. This is number 1, number 2, number 3, parent chain. This is a methyl group and alcohol. Propan, 2-methyl, right? 2-methyl. Second position, there is a methyl group. 2-methyl, propan, 2-ol, right? 2-methyl, propan, 2-ol. So what is your answer? Option C is the correct answer. Okay. Next question. Vapors of an alcohol X. So they given a alcohol X. When passed over hot reduced copper. Hot reduced copper. We studied, no? It is a oxidizing agent. Copper at 573 Kelvin. This is the indirectly meaning. Okay. It produces an alkene. It produces an alkene. What is the alcohol? Actually, The mechanism or the reaction, general reaction we know, primary alcohol on oxidation. You know, copper at 573 is an oxidizing agent. Primary alcohol on oxidation, we will get always aldehyde. Secondary alcohol on oxidation with this reagent, you will get a ketone. But we studied tertiary alcohol will not undergo oxidation generally. But in presence of the oxidizing agent copper at 573 Kelvin, it will undergo dehydration. It will undergo dehydration. By the way, it will give you a alkene. Okay, keep in mind all of you. Generally, primary alcohol on oxidation, we will get aldehyde. Secondary alcohol on oxidation, we will get ketone. Tertiary alcohol generally won't undergo oxidation, but in presence of the oxidizing agent copper at 573 Kelvin, it will give you dehydration, means elimination of water. By the way, it forming an alkene. So what is the answer here? When the vapors of an alcohol X when passed through the copper, which produces an alkene, then which is the alcohol? Your alcohol should be a tertiary alcohol. I will show you one of the reaction in the next question. Here we have, what happens when tertiary butyl alcohol treated with the copper? This is the reaction. Okay, what is tertiary butyl alcohol? This is the one, right? This is the tertiary butyl alcohol. Okay, it is reacting with what? Passed over heated copper. Copper at what is the temperature normally we are carrying out? 573 Kelvin. Yeah, 300 degrees Celsius equal to what? Plus 273, 573 Kelvin. We can write the dehydration. As I told you, this is a tertiary alcohol. When a tertiary alcohol treated with the copper at 573 Kelvin, instead of oxidation, it will prefer dehydration. What is dehydration? OH group you take from alpha carbon, one of the hydrogen you take from beta carbon. All are beta, any of the beta. Okay, OH you take from alpha carbon, one hydrogen you take from beta carbon, eliminate water, make a double bond between alpha beta. Finish. So what is the answer? This is the product you are going to get, plus water. What is the name of this product, dear all? This is 1, 2, 3. This is the parent chain. Second position contain a methyl group. Therefore, 2-methyl. Total 3 carbon in the parent chain. Proper 1-ene. Proper 1-ene or propene. So what is your answer? 2-methyl. 2-methyl. Propene is the answer. Option B is the correct answer. Okay, next question. Here we have, which of the following reagent cannot be used to convert or to oxidize a primary alcohol to aldehyde? As I told you, if you want to convert primary alcohol into aldehyde, we are using total major 3 reagents. What are they? Best one is PCC, or we can use anhydrous CrO3, or we can use copper at 573 Kelvin. Any of them is fine. The best is what? PCC. Okay. So CrO3 is fine? Yes. KMNO4? KMNO4 in acidic medium. Is it possible? No, dear all. KMNO4, K2Cr2O7 all are very strong oxidizing agent. Okay. In the presence of a strong oxidizing agent, primary alcohol directly converted to carboxylic acid. Because you know, aldehyde further oxidation, we will get carboxylic acid. KMNO4 is a strong oxidizing agent, so directly alcohol converted to carboxylic acid. Here we need only up to aldehyde. So which is the best? Pyridinium chlorochromate, PCC fine. Copper at 570, that's also fine. Only the one is not possible, that is KMNO4. Next one. Which of the following compound will be most easily attacked by an electrophile? What is compound A given? Benzene. Okay, benzene. What is compound B given? Chlorobenzene. Okay, chlorobenzene. What is compound C given? Phenol. Okay, phenol. What is compound D given? That is toluene. Okay. You may know how to write the resonance structure and everything. I'm not going to that. This is normal benzene, chlorine. You know that chlorine a halogen directly connected on benzene ring, it acts as a, because of plus R effect, it acts as a electron donating group. Correct. It is a, but it is a weak electron donating group. Why? Because chlorine have a tendency, because it is an electron withdrawing group also. Why it is acting as an electron donating group on benzene ring? Even resonance structure is predominant here. So chlorine is actually having an electron withdrawing tendency, which means minus I effect group is there. At the same time, due to resonance, a little tendency to donate also. Correct. And OH group is a pure electron donating group. Because oxygen containing 2 lone pair, it can give resonance. Toluene, alkyl groups also act as a electron donating group. That is also very weak donating group. You may study the resonance structure. You may study the resonance structure of these kind of species. Correct. What are the resonance structures? You know how to, for example, let me take phenol resonance structure. Okay, a small reference. This is called phenol. Okay, phenol. Oxygen is there, lone pair. When you draw the resonance structure, this lone pair comes here. This pi electron moves this side. So what you will get here all? You will get a structure like OH. There is a lone pair. Oxygen donated on lone pair. So it will get a positive charge. This pi bonded electron moves here. Okay, so it will carry a negative charge. What is the next structure? This lone pair comes here. This bond comes here. So you will get the resonance structure. Alright, OH plus, and where is the new electron here? With a negative charge. Similarly, 2 more structure, you will get it. Okay, I'm not writing all of them, you know that. Here, which of the following compound will be most easily attacked by an electrophile? What is an electrophile? Electrophile is mean electron loving compound, right? Electron loving compound. So electron charge is negative. So what should be the charge of an electrophile? Positive. Positive or electron deficient, right? So electrophile is generally expressed by the symbol E+, because they are electron deficient compound, or they are going to attract an electron. That's a positively charged species generally. Where these positive charges can attack negative position, correct? So in the phenol resonating structure, you can see in the second and third figure, all of you observe, this is ortho position, this is meta position, para position. Can you see on ortho position there is a negative charge and electron richness? Yeah. So electrophile can easily attack this side. Can you see in third structure para position contain electron negative charge? Yes, electrophile can goes to para position also. Therefore, you studied phenol is a ortho para directing group. It will welcome phenol. It can welcome the upcoming electrophile into ortho position and para position. Not only phenol, any electron donating group. If any electron donating group comes on benzene ring, it will act as a ortho para directing group for the upcoming electrophile. Why? When you're drawing the resonance structure, ortho and para positions are electron rich. So electrophile can easily attack. So the question, which is the best electron donating group? Of course, phenol. Right? Phenol, because oxygen contain 2 lone pair, it can easily. Why not chlorine? Chlorine having a electron withdrawing tendency also. It is not a best donating group. Alright, methyl is also less donating group. So the answer is which one? C, compound C. The phenol can undergo electrophilic substitution so easily. Dear all of you, I'm going to the next question. Out of benzene and phenol, alright? What is that? This is benzene and phenol. Out of benzene and phenol, phenol is easily nitrated because, you know what is nitration? Nitration, chlorination, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, all are electrophilic substitution. Correct. So what is that? During nitration, what is the upcoming electrophile? NO2+. During nitration, what is the upcoming electrophile? NO2+. Where this NO2+ can attack? Where this NO2+ will attack? We just discussed before. It is an electrophile. NO2+ is a electrophile. Where electrophile can attack? Where the electron rich position. Where is electron rich position? Where electrophile can easily attack. Benzene, it can show resonance, okay, but still it can make electron richness? No. But phenol, we discussed, phenol is an electron donating group. When we drawing the resonating structure, ortho positions and para position, you can see negative charges or electron richness. So easily electrophile can attack ortho position or para position. Correct? So phenol is the most one because it making OH group making electron richness on benzene ring. So what is your answer, dear all? Presence of OH group in phenol increase the electron density at ortho and para. Of course, option A is the correct answer. Next question, dear all. Picric acid. You know what is mean by picric acid, right? You may study there are two type of nitration. Two type of nitration happening in phenol. Two type of nitration happening in phenol. This is called phenol. You can carry out nitration on phenol in two ways. What are the two nitration? One is mild nitration, one is strong nitration. We are adding, that is, first of all, we are using diluted nitric acid. This is called weak nitration, and we are using concentrated nitric acid. This is called strong nitration. You know, phenol is a ortho-para directing group. So the electrophile, what is the upcoming electrophile during nitration? NO2. NO2 group goes to ortho position and para position. So here we can say that this is a weak nitrating agent, so it will give you two products. What are the two products? One of the nitro group can goes to ortho position, one nitro group goes to para position. So the products are ortho nitrophenol and para nitrophenol when we are using dilute nitric acid. What about strong nitric acid, concentrated? All of the ortho and para positions at a time are filled by nitro group. Ortho, ortho, para. What is the name of this compound? This is the major group. Therefore, this is number 1, 2, 3, 4, 5, 6. 2, 4, 6. Trinitrophenol. 2, 4, 6. Trinitrophenol. That is also known as what? Picric acid. It's a yellow colored substance, correct? Picric acid is also known as what? Yellow colored substance. So what is your answer? What is your answer? Picric acid is a yellow colored compound. What it is? 2,4,6 trinitrophenol. Option B is the correct answer. Next one. Phenol when treated with excess bromine water. You studied total there are two bromination in phenol, right? There are two bromination on phenol. What are the two reaction? First of all, I am taking phenol. We can do here weak bromination and strong bromination. Okay, first I am doing weak bromination. If you want to carry out weak bromination, the reagent is bromine in presence of carbon disulfide. If you want strong bromination, we can use bromine water. Same like previous case, nitration, you will get the product. If you are using mild bromination, you will get two products. What are the two products? Orthobromophenol and we will get parabromophenols. If you are using bromine water, at a time, all the ortho and para positions are occupied by bromine. So what is the name? 2,4,6 tribromophenol. You have studied that. It's a white colored substance. So what is your answer? Here what they are using? Bromine water they are using, dear student. So your answer is what? 2,4,6 tribromophenol. Option A is the correct answer. Okay, next one. What is the major product obtained on interaction of phenol with sodium hydroxide and carbon dioxide? You may study this reaction. Phenol first treated with aqueous NaOH. What will happen? From OH and OH will eliminate and you will get the compound which one? ONA, sodium phenoxide. Sodium phenoxide, they are treated with which one? So the major product obtained on interaction of phenol with the sodium hydroxide. Okay, that's over. Phenol when treated with the sodium hydroxide, we will get sodium phenoxide. Okay. And carbon dioxide, you may study then treated with the carbon dioxide and then acid. What is, dear student? You remember? This is what? Alcohol. On the ortho position, there is a carboxylic acid. Phenol with a COOH group on ortho position is called what? Salicylic acid. Salicylic acid, right? What is this compound? Salicylic acid. You may study it. It's a naming reaction. The conversion of phenol into salicylic acid or phenol with the carbon dioxide. Phenol with the carbon dioxide, only one reaction we are discussing. That is Kolb's reaction. This reaction is called what? Kolb's reaction. Conversion of phenol into salicylic acid is called Kolb's reaction. What is the conversion of phenol into salicyl aldehyde is called Reimer-Tiemann reaction. Keep in mind. Okay, so what is the major product here, dear all? Salicylic acid, right? Option C, salicylic acid is the major product. This is Kolb's reaction. Now, conversion of phenol into salicylic acid. Phenol into salicylic acid, what is the name of reaction we said? Kolb's reaction. And to salicyl aldehyde. Phenol into salicyl aldehyde. What is the name of the reaction? Reimer-Tiemann reaction. That's a question. So phenol to salicylic acid is Kolb's reaction. Phenol to salicyl aldehyde is which one? Reimer-Tiemann reaction. I think option D is the correct answer, right? Kolb's and Reimer-Tiemann. Then there is a conversion question is given here, dear all. What is the starting material? Phenol. Phenol treating with what? That already we discussed. Bromine in presence of carbon disulfide. You know, bromine in presence of carbon disulfide is bromination. So bromine group is coming. Bromine electrophile is coming here. What is the majority? What is the discussion here? This is a weak bromination, right? You know, alcohol is a ortho-para directing group. Alcohol is a ortho-para directing group. So what will happen in this case? What will happen in this case? Bromine comes to ortho position and also bromine comes to para position because alcohol is an ortho-para directing group. Okay, these are the product. You are getting as X. What is the second reaction? Down. First they treated with chloroform and aqueous NaOH. Second, treated with the dilute acid. What is this reaction, dear student? Phenol reacting with the aqueous NaOH and chloroform. That is our Reimer-Tiemann reaction. So what is during Reimer-Tiemann reaction your product? Salicyl aldehyde. Here instead of acid, this is aldehyde. This is called salicyl aldehyde. So what are their product? Here X compound is ortho and para bromophenol. Y compound is salicyl aldehyde. Option B is the correct one. Alright. Next one. Identify the final product in the following reaction. What is the starting material? Phenol. Starting with the phenol, we are using zinc. You know, zinc is a reducing agent. So what will happen here? The zinc will go with this oxygen atom as zinc oxide. When phenol treated with zinc, what is your product? Benzene, right? Benzene. Phenol on reduction with zinc, you will get benzene. Now, so this is your compound X. This compound treated with what? CH3COCl acyl or acetyl chloride in presence of N-hydrous AlCl3. What is the addition of an acyl chloride with N-hydrous Cl3? AlCl3 is called Friedel-Crafts acylation. Correct or not? During Friedel-Crafts acylation, what is the upcoming electrophile? CH3CO+. That is the upcoming electrophile. So you just add this group to benzene ring. Benzene with COCH3. What is benzene with the COCH3 is called? Acetophenone. Benzene with the COCH3 is called acetophenone. Correct or not? So what is your answer? Option B is the correct answer. So first one, phenol on reduction, you will get benzene. Benzene on Friedel-Crafts acylation, you are getting acetophenone. Is it benzophenone? No. Right. What is benzophenone, dear all? Benzophenone means benzene with the CO, then another one. Right. This is called benzophenone. Not the correct answer. Next one. Benzoquinone prepared by the reaction of phenol with. You may study just the reduction of phenol, oxidation of phenol. What is the oxidation of phenol? You know, phenol means benzene with the OH. Phenol on oxidation with the Na2Cr2O7 is called chromic acid. Na2Cr2O7. Dear student, in the previous case we studied reduction. Phenol on reduction with the zinc, you are getting benzene. This is oxidation of phenol. Phenol on oxidation with the chromic acid with the sulfuric acid, H2SO4, you are getting benzoquinone. What is benzoquinone? Two double bonds like this and one ketone here, one ketone here. This is called benzoquinone. So phenol you can on oxidation, phenol on oxidation you will get benzoquinone. So what is the reagent we are using? Na2Cr2O7, chromic acid with the sulfuric acid. Alright, option A is the correct answer. Next question dear all, look very carefully. A primary alcohol C3H8O. Primary alcohol C3H8O. You know C3, which means there are 3 carbon, correct? 3 carbon. They already said it is a primary alcohol. 3 carbon containing the only one primary alcohol, right? What is that? We can say propanol, right? Yeah, propanol. What is propanol? CH3, CH2, CH2OH. This is called what? Propanol. So this is your starting material, compound number A. What compound number A does here? Compound number A on heating with sulfuric acid. You know sulfuric acid, it is a dehydrating agent. Alcohol will undergo dehydration. What is dehydration? Alcohol you take from alpha carbon, hydrogen you take from beta carbon, put a double bond between alpha beta. So the product is CH3, CH double bond, CH2. Propene. Propene is the product. Undergo dehydration to give an alkene. This is compound B. Okay, not over. B when treated with HCl, B when treated with HCl, you are getting a compound C. That's treated with HCl, okay? This is an alkene, HCl. Can we follow Markovnikov's rule? Yeah, there is no peroxide, right? We can follow Markovnikov's rule. What is Markovnikov rule? Negative part will goes to carbon contain less number of hydrogen, positive with a more number of hydrogen. Product will be CH3, CHCl, CH3. What is this compound? 2-chloropropane. Okay, I think product reaction is not over. What is the next reaction? This compound C on treating with the aqueous KOH. You know aqueous KOH mean nucleophilic substitution. What is the upcoming nucleophile here? OH minus, right? OH minus attack to this instead of this chlorine. Chlorine will leave, OH nucleophile will substitute. You will get what? CH3, CHOH, CH3. That is your compound D. Question: what is the relation between A and D? What is A? What is A? A compound is propan-1-ol. What is compound D? Propan-2-ol. Propan-1-ol and propan-2-ol. What is the difference? Their position of the functional group OH is different. They are having same molecular formula, but the position of their functional groups are different. Which isomer? Position isomerism. Position isomerism, right? Compound option B is the correct answer. Next one, dear all. Let's go here. Consider the following reaction, identify the product. What is the starting material? We can go with phenol. For their first using zinc, what we studied, phenol on treated with a zinc, reduction will happen. Zinc will go with this oxygen as zinc oxide. Your product is benzene. This is your compound X. This compound treated with a methyl chloride in presence of anhydrous AlCl3. What is this reaction? Addition of a haloalkane in presence of anhydrous AlCl3, Friedel-Crafts alkylation. What is the upcoming electrophile? CH3 plus. Add into benzene ring, you will get benzene with the CH3. We will call it as toluene. You know that is compound Y. This is treated with alkaline KMnO4. Dear all, alkaline KMnO4 is a very strong oxidizing agent. Alkaline KMnO4 is a very strong oxidizing agent. It will convert whatever the alkyl group on benzene ring, directly it is converted to carboxylic acid. So alkaline KMnO4, CH3 converted to COOH. What is benzene with the acid is called benzoic acid or benzenoic acid, right? So benzoic acid, option B is the final product Z. Final product Z. Alright, next question here we have, okay, very simple question here. Column number 1, they given so many reaction. What is the name of the reaction? Very simple. Can you able to see that? This is what? Phenol. Phenol treating with what? Haloalkane. Just we discuss now. Phenol when treated with the haloalkane in presence of anhydrous AlCl3. You know, this is the upcoming electrophile. You know, phenol is a ortho-para directing group. So, where this electrophile will attack to the ortho position and para position. Yeah, ortho and para. Ortho-methyl phenol, para-methyl phenol. What is this reaction? Friedel-Crafts alkylation. Where is Friedel-Crafts? This is the A1. So, A with the A matching with the 2. A matching with the 2. That is only one answer. Option B. Anyway, we can discuss the others also. What about here? Phenol treating with the NaOH chloroform. Phenol treating with the NaOH chloroform. We will get salicylaldehyde. Salicylaldehyde preparation is called Remer-Tiemann reaction. Remer-Tiemann reaction. This is B. And what about C? C is what? Phenol treating with the NaOH carbon dioxide. It is giving you salicylic acid. What is the reaction? Kolb's reaction. Kolb's reaction. What is the last one? This is a salicylic acid treating with the NaOH and calcium oxide. This actually is studying in the next organic chapter, aldehydes ketones. Okay, anyway, you studied in 11th grade also. This is carboxylic acid, NaOH and calcium oxide. Sodium hydroxide, calcium oxide is known as what? Soda lime. So what is happening? This carbon dioxide part is removing from the system. You will get phenol. This is called decarboxylation process. That is called compound D. So your overall answer is option number B. Next question, dear all, we have ethers is obtained from ethyl alcohol in presence of sulfuric acid at what temperature? You studied one of the reaction in textbook. You can see the first method of preparation of ether. This is what? Normal ethanol. Normal ethanol, when we heated with the concentrated sulfuric acid at 443 Kelvin. Same thing I am using here, concentrated sulfuric acid at 413 Kelvin. Two reactions are happening. If you are carrying ethanol with the 443 Kelvin with the sulfuric acid, it will undergo dehydration. Dehydration means you will get ethene plus water. The same thing if you carried out at 413 Kelvin, you will get ethoxyethane. That is the ether. Ethoxyethane. So what is the data you are getting here? When you heat a alcohol with a 443 Kelvin, we are getting alkene, dehydration. At a 413 Kelvin, it giving you ether. So if you want to get ethers from alcohol, you have to heat with what temperature? 413 Kelvin. Okay. Next one. Ethers are prepared by the reaction of sodium alkoxide and alkyl halide. That is called Williamson synthesis. Which of the following reagents should be taken to prepare methyl tert-butyl ether? What is actually your ether? Methyl, okay. Tert-butyl. What is tert-butyl? This is the one called tert-butyl. And there is a ether. This is the compound we have. If you want to get is ether, which reaction we have to carry out? Let's see. Compound number A. What is compound A given? Tert-butyl bromide. Tert-butyl bromide reacting with what? NaOCH3. What is this? Sodium methoxide. Will you get the product? Will you get the product, dear all? No. See the textbook very carefully. This is a tertiary butyl bromide. This is a haloalkane. This is sodium alkoxide, sodium methoxide. A very simple trick, let me tell you, a simple idea, only a direct idea. You know, actually, most of the students, they will try to remove bromine and sodium. They will club it. You will say, yeah, I'm getting this ether. This is not Williamson synthesis. Williamson synthesis mean, try to remember, if you want to get an ether, your haloalkane part should be a smaller one. Your sodium alkoxide part should be a bulky one, bigger one. A small idea, okay? Your haloalkane should be a smaller group. Your sodium alkoxide part should be a bulky group. This is just opposite, right? What is the problem? If your sodium alkoxide group is a smaller group, it can act as a nucleophile. At the same time, it is a strong base. If your sodium alkoxide group is a smaller group, it will act as a strong base also. In presence of a strong base, haloalkane will not undergo Williamson synthesis. It will prefer to undergo beta elimination reaction. You know, what is the normal thing you are using for beta elimination? Alcoholic KOH. Why you are using alcoholic KOH? Because it is a strong base. So here we have a strong base. In presence of a strong base, this will undergo beta elimination. So let me write what is the answer for beta elimination. What is beta elimination, dear all? Dehydrohalogenation. Halogen will go from alpha carbon. One hydrogen will go from beta carbon. Put a double bond between alpha beta. This is the product you are going to get. Yes? Yeah. This is the product you are going to get. This is an alkene, not this product. So first one is not possible. What about B? B compound. CH3Br haloalkane. NaOCCH3CH3CH3 tertbutyl sodium tertbutoxide. Here it is possible? Yes. As I told you, if you want to perform Williamson synthesis, what is Williamson synthesis? A haloalkane reacting with the sodium alkoxide, NaBr eliminate, club it. Here it is possible. Why? I told you, if you want to get Williamson synthesis, your haloalkane part keep it as a smaller group. Sodium alkoxide part make it as a bigger group. Why? You know, Na plus is there, O minus is there. If your sodium alkoxide part is a bulky group, it can just act as a nucleophile. It will act as only a nucleophile. It is not a strong base. But what about the previous condition? NaOCH3 is a smaller group. Here, Na plus O minus, this nucleophile, this is a strong base also. In presence of a strong base, which reaction will happen? Beta elimination. In presence of a nucleophile, the Williamson synthesis happen. What is Williamson synthesis? Very simple. This NaBr you eliminated, club the remaining compound. CH3, O, CCH3, CH3, CH3. Are you getting your product? Yes. So option B is the best method to get the product. Okay, keep in mind, very carefully read NCERT textbook under the region Williamson synthesis. You can see the same reactions. Next question, dear all, we have what is complete the following reaction. What is the reaction? Starting material is CH3CHBr CH3. This is compound X. 2-bromopropane. It is treated with alcoholic KOH. What is mean by alcoholic KOH purpose in organic chemistry? In alcoholic KOH we are using for beta elimination. It is a strong base. Beta elimination. What is beta elimination? Halogen, take it from alpha carbon. One hydrogen you take from beta carbon. Make a double bond between alpha beta. So your product is which one? Propene. Propene. This is compound Y. Okay, let's carry out. Reaction not over. Let's go. Here we have treated with the HBr in presence of peroxide. Careful. Addition of HBr in presence of peroxide, we can follow anti-Markovnikov rule. Anti-Markovnikov rule. What is anti-Markovnikov rule? Negative part will goes to carbon with a more number of hydrogen. Positive part will goes to carbon with a less number of hydrogen. We will get the compound 1-bromopropane, right? 1-bromopropane. This is your compound. Which one? Z. Not Z, right? Sorry. This is the compound. I think this is the compound X. Z is the final product, right? This is the compound X. This is the compound Y. Finally, we are going to prepare Z. What is Z? We are taking CH3ONA. This is a haloalkane. This is sodium alkoxide, sodium methoxide. Haloalkane with a sodium alkoxide is called Williamson synthesis. Here can we follow Williamson synthesis? Yes, because you see here haloalkane is a smaller one and sodium alkoxide is also a smaller one. So in these kind of cases, if they both are almost a similar type, you can easily perform which one? The Williamson synthesis. So what is happen? This NaBr will eliminate, OCH3 will substitute here. So CH3, CH2, CH2, OCH3 can be the product. Ether. So what is your answer? This is a compound Z. Where is X? Where is X? CH3, CH double bond, CH2, all are X. Which is Y? 1 bromopropane. Where is 1 bromopropane here? Option 2 or option D? Which is this product? CH3, CH2, CH2, OCH3, right? Option D is the correct answer. So first one, beta elimination in presence of alcoholic KOH. Second reaction, anti-Markovnikov's rule. Third reaction, Williamson synthesis. Next one, ethers have lower boiling point. Let me take a smallest ether, methoxymethane, CH3OCH3. Then the corresponding isomeric alcohol. So this is 2 carbon, right? Therefore 2 carbon containing alcohol is ethanol. This is ether, this is alcohol. Why ethers having low boiling point and why alcohols having greater boiling point? We know alcohols are connected through very strong intermolecular hydrogen bonding. Correct? Intermolecular hydrogen bonding. So alcohols having intermolecular hydrogen bonding, but ethers cannot show that much. So what is your answer? Hydrogen bonding in alcohol that is absent in ether due to low polarity. Yes. If there is a strong hydrogen bond, they're having strong boiling point. So alcohols having greater boiling point compared to ethers. Next, dear student, we have the question. Which of the following are the product shown by the reaction of methoxyethane with the hydrogen iodide? What is methoxyethane? Methoxyethane, right? Methoxyethane we have. It is treating with what? Hydrogen iodide. You know, the splitting of CO bond in ether. Hydrogen iodide means there are 2 species, H plus and I minus. If you want to react H plus and I minus here also we need a anion and cation. If you want, either you can break this CO bond or you can break this CO bond. You may study, if there is a primary group left and primary group right side, we will follow SN2 mechanism. We will follow SN2 mechanism. Where is the less steric crowded area? That part you have to break it. Which is the less crowded area? There is 2 carbon, here 1 carbon. This is the less crowded area. You have to break here. If you break this one, oxygen always carry negative charge, so carbon carry positive charge. Now you just make a double displacement to the CH3 plus, I minus will attack. Product is CH3I plus. To the ethoxy group, to the IO minus, H plus will attack. So you will get ethanol. What is the principle, all of you? If there is a primary group and primary group, the middle of this oxygen is at the middle, primary group or primary secondary group or primary secondary, if this kind of group comes, you have to follow SN2 mechanism. For example, I'm taking CH3, CH, CH3, O, CH2, CH3. Which group present left side of this oxygen? A secondary group. What is secondary? The carbon connected to 2 carbon, secondary. Here it is connected to primary. This carbon connected to 1 carbon, primary. In these cases also, primary, secondary, primary, secondary. In these cases, mainly you have to follow which mechanism? SN2 mechanism. In SN2 mechanism, you know, you have to break the less crowded carbon-oxygen bond. So which is the less crowded carbon? Here there are 3 carbon, here only 2 carbon. This is the less crowded part, break here. This is O minus plus. Now interchange it. Okay, so what is the answer here? Here we are getting CH3I and CH3CH2OH. Option D is the correct answer. So the cleavage of CO bond in ether is important. Let's study some more question here. Okay, in the reaction, see the reaction, this is what? Benzene with OCH3. What is benzene with the OCH3 is called? anisole. What it is called? Anisole. Correct. Anisole, here it is treating with the HBr. You know, this is a aromatic ether, benzene containing ether. Here H plus is there, Br minus is there. Can you make a ion in this anisole? Where you will break? Either you can break this OC bond or you can break this OC bond. Which will you break? Dear all, in aromatic ether, benzene containing ether, after the breaking of CO bond, keep in mind, after the breaking of CO bond, you should get phenoxide ion. In an aromatic ether, after breaking the CO bond, you should get a phenoxide ion. What is a phenoxide ion? Benzene with O minus. If you want to get this ion, which bond you can break it? Whether this or this. This one you have to break it, right? So this is O minus CH3 plus. Make your product benzene which contain O minus. To the O minus, what will attack? Phenol. And plus CH3 plus with a Br. CH3Br. So keep in mind all of you. In the previous case, primary, secondary, primary, those kind of group when comes, where is less crowdiness, that bond try to break it. What about tertiary? If a tertiary group comes, no confusion dear all. So okay, this is a tertiary group, this is a primary group. This is tertiary, this is primary. In such a kind of group, when you're adding a HBr, HI something, which bond you will break it? Tertiary, if it is there, no confusion, break the tertiary part. Which is the tertiary part? This one. Tertiary, if it is there, no confusion, break the tertiary part. So this is O minus, this is plus. So to the plus part, what will comes? I will come. To the O minus, H will come. Okay, so tertiary group, if it is there, try to break the tertiary part because it will follow SN1 mechanism. You know, SN1, tertiary, if it is there, it will prefer SN1 mechanism. SN1 mechanism follows the stability of carbocation. So tertiary is the most stable. Okay. So these group, smaller group when comes, like a primary, secondary comes, follow SN2 mechanism. Tertiary when comes, follow SN1 mechanism. Okay. So your answer is which one? The aromatic ether when comes, you just keep in mind almost follow SN1 mechanism here. Here after the breaking you should get phenoxide ion. So what is the product? Phenol and CH3Br. Option D is the product. Okay. Now anisole on reaction. What is anisole again? Benzene with OCH3. Okay. This is anisole. Anisole on reaction with chloromethane in presence of anhydrous AlCl3. What is chloromethane dear all? CH3Cl in presence of anhydrous AlCl3. What is this reaction name? Addition of a haloalkane with anhydrous AlCl3. Friedel-Crafts alkylation. What is the upcoming electrophile? CH3 plus. Where this CH3 alkyl group can add? That depends on OCH3. Methoxy. Generally, alkoxy groups are ortho-para directing group like phenol. So, CH3 group can goes to ortho position and para position. So, what are the product? You will get two product dear all. This is anisole. This is anisole. CH3 can goes to ortho position, CH3 can goes to para position. So what are the product? Ortho-methyl anisole, para-methyl anisole are the product. That's the thing is this one. Anisole is a ortho-para directing group. So what is the answer? Ortho-methyl anisole and para-methyl anisole. Okay. Careful. Ortho-methyl anisole and para-methyl anisole. Option C is the correct answer, right? Ortho-methyl anisole and para-methyl anisole. Okay. Next one. What is the correct order of the reactivity of alcohol in the following reaction? Alcohol reacting with the hydrogen halide in the zinc chloride. What is hydrogen chloride with the zinc chloride is called? That is our Lucas reagent. You know Lucas reagent which is giving high product, right? Which is giving immediate reaction. Tertiary greater than, secondary greater than, primary. Tertiary, secondary, primary. Lucas reagent is more given by tertiary, least given by primary. Okay, we have the last question in our part 1 video for the alcohol, phenol and ether chapter, the 50th question. Monochlorination of toluene. What is toluene? We have benzene with CH3. This is called toluene. Monochlorination. Okay. Toluene in sunlight. In sunlight, you're adding Cl2, right? Chlorination means addition of chlorine in presence of light. Light means you write H nu. Okay, fine. Followed by hydrolysis by aqueous KOH. So the getting product, you are hydrolyzed by treating with which one? Aqueous NaOH. Okay, aqueous NaOH. Fine. Yield. What is the product? Dear all, this is toluene. You are doing chlorination. Okay. Toluene can undergo two types of chlorination. This is what? In presence of light. In presence of light, it will undergo substitution reaction. Correct? Substitution takes place on alkyne chain. Alkyne, right? Alkane chain. Yes or no? Substitution will happen on alkane chain, not in benzene ring. So what is substitution? One hydrogen will go with one chlorine as HCl. Remaining chlorine attached to instead of hydrogen. So you will get the compound benzene with CH2Cl. Substitution in presence of light. Light means substitution you have to done only on alkane chain. Okay, not please don't add into benzene ring. What is the answer? What is the name of this compound? Benzene with a CH2 is called benzyl with a chlorine. Therefore, it is called benzyl chloride. Alright, benzyl chloride. Now, treating with the aqueous NaOH, nucleophilic substitution, NaCl will eliminate, OH nucleophile will substitute. What you are getting? Benzyl group with an alcohol. That is called what? Benzyl alcohol. Your answer is option A. Now, I told you toluene undergo two types of chlorination. This is in presence of light. Where you want to add chlorine? On alkane chain. Another one, let me remind you, addition of chlorine in presence of a catalyst, FeCl3, not light. In presence of chlorine, in presence of a catalyst, if you are adding, this is electrophilic substitution. What is the upcoming electrophile? Cl+. Cl+ is coming. Where Cl+ will attack? It is an electrophile, right? It will go to benzene ring. You know, CH3 is a ortho-para directing group. So you will get two product here all. You will get chlorine on ortho position, chlorine on para position. So keep in mind very carefully, if toluene they given, if you are performing chlorination in presence of light mean, please add chlorine into the alkane chain. If it is in presence of the catalyst like FeCl3, please add into ortho and para position. Okay. So hope you clear the 50 questions from the chapter alcohol, phenols and ether. We will meet again with 50 more questions, 50 more important questions with so much theory discussion in the part 2 session for the same chapter alcohol, phenols and ether. Okay, bye all of you. So wish you all the best for your upcoming term 1 examination. Keep practicing. We can make a good result. Thank you all.